Okay, so now having discussed the kinds of basis functions, we will look at, we'll try to understand this method in more detail, and the simplest example is a 1D example. Okay, so we'll work through how do we set up the equations, convert it into something called a weak form, which is very characteristic to FEM. I'll tell you what that is, and then how do we solve it. Okay, so the equation setup. Now, on the board over here, I have written a very generic differential equation. Okay, so in this differential equation, your unknowns are what you want to find out are given is u of x. Okay, and knowns are p of x, q of x, and f of x. These are given to you. Okay. Now, why have I chosen a differential equation like this to start off with? So, first of all, those of you who remember from your math courses, this differential equation looks very similar to the Sturm-Liouville differential equation, if you remember it. Not exactly, there are some extra terms in that equation which are not over here, but I mean the left hand side structure looks similar. And the power of that is it allows you to express almost any second order differential equation in this generic form. Okay. So, we will take, I mean I will show you two examples. So, for example, a parallel plate capacitor, a DC problem. So, for a DC problem, what is the, you have a charge and you want to find out voltage, that is your DC problem. So, that is also called as which equation? Given a charge, find out the potential everywhere. Statics, Laplace equation, right? That was your del squared V is equal to minus rho by epsilon, right? So, this parallel plate capacitor, which looks something like this, that you have a capacitor, infinite capacitor in both directions. This is, let us say, grounded, and this is at some voltage V. Okay. You want to solve a problem like this. So, over here, say u of x is the potential. Okay, this is your x. Okay. And potential. What about the potential at this point? So, u of 0 is going to be 0, it is a grounded plate, and the upper plate is maintained at some voltage V naught, and you want to find out how does the potential vary as I go through the capacitor. That is one something that you might want to calculate, right. So, I know that the differential equation is this. So, can I fit it into this generic form? I can, right. So, what would I have to do? So, for example, what will be the value of Px? Px will be minus 1, correct. Then what is next? Qx. Qx will be 0, okay. And then f of x will be minus rho by epsilon, right. So, then that will become d by dx, du by dx is equal to minus rho by epsilon. Okay. So, nothing new here, just saying that this generic looking equation can capture a lot of problems in electromagnetics, that is why we sort of look at it. Okay. Then you also another problem, the second problem I will take. So, one was parallel plate, the other is a wave between parallel plates. Okay. The equation for this you have already studied, it is the Helmholtz equation, right. A wave equation is the Helmholtz equation, and we know that the Helmholtz equation is something like E double prime plus k naught squared E is equal to what? Some constant times the current. We have seen this equation many times. So, how do I get this equation in this form? So actually P, yeah, it would be tempting to set P equal to -1, but remember epsilon r and mu r need not be constants, right? So the same trick that we had to do to use eliminate H from Maxwell's equations, we had to take a 1 by mu r, right? So this P of x will in fact be -1 by mu r, okay. So the first term will become like this, okay. Second term k naught squared with one more thing, one more material property, epsilon r, exactly, epsilon r E is equal to Fx, whatever the current source is on the right. So my P was this, my Q was k naught squared epsilon r. Okay, so this is the sort of a general differential equation which is used many times. Okay, fairly straightforward. One thing is that the boundary conditions are there; they have to be obeyed and respected. We at x equal to 0 and x equal to xa, and that will be important, and we'll see how it goes. Alright. So now let's put it into the FEM framework. So FEM, another word we had said was weighted residual method, correct? So first of all, for weighted residual, I must define the residual. So this was my differential equation, right? So the residual is what? Left hand side minus right hand side is called residual. So this residual r of x is defined as left hand side minus right hand side, okay. And then what do I want to do? Weighted residual method. So I have to take the integral of some weighting function, I will call it Wm, multiplied by r of x, integrate over dx, and set it equal to 0. That becomes the weighted residual method, okay. So earlier I had called this as the basis function Bm, okay. I am just calling it W because W is coming from the word weighted, okay. So W, so this is your weight function or basis function or testing function. These are all the different words used for it. Another word is, you will find trial function. Everyone comes up with their own word for it, okay. They all mean the same thing, okay. What is the domain of integration? Is the support of Wm. Remember, so Wm, for example, in the 1D case is, so Wm is not a node, but it's the function defined on the segment, on the mth segment, right. So it's a function, and it's non-zero only within the segment, 0 everywhere else outside it, okay. That's how it looks like. Okay, so let's sort of visualize this a little bit better. So it's a 1D problem, so I should draw a line. Shape functions, right? W will be the shape functions. Why? Because we are going to do what is called Galerkin's method, where the basis function and the testing function are the same, right? Okay, so let's call these like this, right? So this is my x1 is equal to 0, right? So now the unknowns over here, I can call it U2, right. So there is U1, U2, U3 and so on, correct. So U2 is what I will call the global name for unknown, correct. There are so many nodes, each one, if there are n nodes, each one is U1, U2, U3 up to UN, those are the unknowns, right. Now in terms of local names, what can I call it? Local names. So for example, if this is the E is equal to 1, this is E is equal to 2, okay. So I will call this over here U. So I am referring to this segment or this segment, right? So can I refer to it like this? So superscript is E is equal to 1. E is equal to 1. So every element has two unknowns, the left node value and the right node value. Left node value I called as 1, right node value I called as 2. So it's E is equal to 1, and for E is equal to 1, that is this guy, which is it, the left or right node? X2 is the right node. So I called it U2 E is equal to 1. I could also call it E is equal to 2. What will I call it in E is equal to 2? Is it the left node or right node? Left node. And this is all equal to, at the subscript. So the same unknown is being called by three different names. It may seem unnecessary to do it, but it actually is phenomenally helpful in coding, because you have a local naming convention and then you have a mapping to global naming convention. When I do it on pen and paper for 3 nodes, 4 nodes, it seems very unnecessary. But when you write a code that should work for millions of elements, it's very, very necessary. Okay, so it will look a little silly at first. Why is this U1, U2? Why have this U1E, U2E, all of that? But it becomes very helpful to systematically form your system. Form your equations.
Why it is equal to U2?
U2 is the global name I am giving to it. No, so this is a local name, only a local name.
U2 at E is equals to 1.
U2
At E is equals to 1.
No, the U2, this 2 refers to left or right.
That 2 refers to the number, right? U1.
And this refers to the global number.
That subscript 2 is what?
That's what the subscript 2 over here. If there is no element over here on top, then it refers to the global number. How many nodes are there? 3 nodes, U1, U2, U3. But if I am referring inside locally, then this refers to L or R. So a better, yeah, if I have 10,000 elements, then I'll have to be numbering them U1 up to U100. But if I am maintaining a list of elements, then within each element there are only 2, U1 or U2. You could write it as UL and UR, but then when you go to code it, right, U1, U2 becomes natural indexes for an array, right? Yeah, so this is something to keep in mind, left or right. Okay, so these are this mapping between local and global should be maintained. Okay, so typically there is some data structure that you will use to maintain this mapping. So what does this mapping tell you? If you give me the global number, you should be able to go in and tell me what are the local numbers. Similarly, if you give me the local numbers, there is a mapping that will go and tell you the global number. So these are implementation issues. When you implement your code, you should have this functionality. Okay. So now one thing I want to mention over here about the choice of these W. Okay, so over here we did not impose any requirements on WM so far, right? So what I spoke about so far was the weighted residual method. I'll briefly mention what are the requirements on WM. Okay, can WM be anything? For example, can it be a pulse basis function or something like that, right? So there are at the very minimum there are 2 requirements on WM. So requirements, so I mean WMX and its derivative, these should be square integrable over the domain. So, I mean, there's not two requirements, there's requirement on u and its derivative. So, implies that, so what does it mean? So, for example, if I take Wmx, square it, and I take the derivative, this should be bounded. Okay, we are not going into the derivation of why this is required, but you can just take it as a statement of fact.
Is it not over omega m?
That is assumed, because Wm will be 0 outside omega m anyway, so I may as well just write it for the entire domain. So, over this entire domain, this W should be, W and this derivative should be square integrable, right. So, the reason, so as I mentioned, we are not going into the reasoning, but the logic is similar to, for example, representing a function using its Fourier series, right. The function there needed to be square integrable and so on, right. So, similar idea. When this is satisfied, it is possible to prove that the FEM system of equations rigorously gives the solution. The system of equations that FEM gives will converge to the correct solution under this guarantee, I mean under this requirement, okay. In addition, yeah, actually I was right, there are two conditions. This is the first requirement. Second is a easier requirement, which is that Wmx must obey the boundary conditions. So, just as an example, supposing the problem had Dirichlet boundary conditions, which said that x1 and xn, the final node over here, xn, is 0. Okay. So, I am giving you boundary condition is that the solution should be u of 1 equal to 0, u of n equal to 0. Can I use the pulse basis functions? I can't, I mean, because the basis functions themselves are not satisfying the boundary conditions. It's not enough that I just attach a weight next to it which is 0, but the basis function itself is not satisfying the boundary condition. On the other hand, if I had a triangle starting from 0, then it is fine. Okay. So, that is just a small example, but these are the two main requirements you have to keep in mind. Typically, we are not in the business of constructing new basis functions. So, we are going to use well known basis functions. These requirements have already been satisfied. We will not waste time in trying to check them. We will just use them. Will be forced to be 0, right. So, it's not a wise choice of basis function to begin with. Fine. So, we'll take a pause at this point. Okay. So far clear? It can be whatever you want it to be. I mean, Galerkin simply means that the testing function W and the basis function for U is the same. So, you can take a Lagrange interpolating polynomial like what we saw for both the basis and testing.
Yeah, so for that, all these conditions are satisfied.
Yeah, yeah. For a Lagrange polynomial, yes, they are satisfied.